Hello everyone and welcome to today's webinar, Solving Today's Automation Challenges with Siemens Virtual Commissioning Software. My name is Sarah Alspaugh and I will be your webinar host. And I would like to welcome and introduce our speaker today. With us we have Gail Sneer. He is a product owner here at Siemens. He directs software development for virtual commissioning within the 3D simulation product group. Gail joined Siemens in 2013 and worked in the engineering team before joining the product management team. He received his BSc degree in mechanical engineering from Tel Aviv University with a special focus on automation and control. All right, well, welcome, Gail. We're so excited to have you here today.
Hello, everyone. Today, I want to talk to you about how we in Siemens view challenges and solutions for automation using virtual commissioning and how Siemens software can help live up to those challenges for today's manufacturing. In order to talk about this, let's actually go a little bit back in time first to early manufacturing. When mass production just started out, it looked a little bit like this. It was very manual and also very rigid. We could mass produce parts, but really only a single part or a couple of parts. Any change in production, like introducing a second part, was very hard to make and also very expensive. As automation came into play, we were able to take many repetitive tasks and automate them. For example, using robots. This allowed for high rate production with great accuracy and consistency, but production still remained very rigid. Implementing any sort of change was still very expensive, and one would have to, for example, reprogram all the robots in a production facility. Another option which evolved with the introduction of IT or MES systems was flexible production, which allowed much greater flexibility in terms of production execution or production planning, but was still very dependent on manual labor. This meant high costs and expertise needed, and also meant slower manufacturing rates. But today's products, and by extension production, must become something else. They have to be kept automated, but require a lot more flexibility and much faster reaction times to changes, both in their planning and in their own execution. The reason is that the market has new requirements. Our customers want their product to be customized, have a good price, come with good quality, and be delivered to them yesterday. Therefore, manufacturing has to change as well. Advanced robotics is considered as one key to enabling addressing the needs in manufacturing. So we'll include this topic in our discussion today as well. On the other hand, manufacturers often lack the direction or ability to achieve their vision. According to the Boston Consulting Group's robotics survey from 2019, more than 80% of companies want to use advanced robotics, but less than a quarter of them have taken any real actions at the time. This is still true today. Apparently, there's a huge gap between the wanted and the reality. So the need is there, but alongside this need, we have great complexity. We in Siemens believe in providing unique tools to build competitive advantage from complexity. To realize this vision, it's clear to us that there are three business imperatives that every customer must embrace in order to turn this complexity into an advantage or operational excellence. First, it's a comprehensive digital twin. This digital twin must be two things. It must cover the entire product or production lifecycle, and it must include a closed loop to ensure that actual performance data is fed back into it from models that are currently being deployed in production. Secondly, companies have to take a personalized approach. There are so many paths a company can take into virtual commissioning. A single approach or a single tool or method won't work for everybody. A company must be able to progress at its own pace in embracing digitization in order to meet needs and gain operational performance. Your engineers, especially younger generations, are very used to already having a personalized experience in everything they do related to software and applications. They expect the same at work, and taking such a personalized approach can really help make people a lot more efficient. And finally, no organization exists by itself. Digitalization extends throughout the entire industrial ecosystem. Collaboration between organizations and individuals is a mandatory step. Manufacturing requires a huge network of suppliers, customers, and partners, all working together effectively. Traditional systems, which are closed, will not work in this new facility. They will create barriers on this road to production excellence. Open systems must be deployed in order to achieve a flexible open ecosystem. Let's talk about this digital twin for a minute. A digital twin is a virtual or a digital copy of production. It enables us to carry out various tasks in a virtual, remote, low-cost, and risk-free environment. It's a great enabler for addressing the multiple challenges in today's manufacturing. One key is to use the digital twin in all stages of production, ranging from requirement specification all the way through to the product's life cycle and even into maintenance and even service areas. You can see various examples of using the digital twin along a typical project timeline on this slide. For example, offline programming of robots, operator training in a virtual environment, or the validation of changes that occur in the real facility in the plant using tools like point cloud scans. Using the digital twin throughout the entire product lifecycle can and has to be a common practice, regardless of whether we're building a new facility or a new line, or retrofitting and improving an existing one. A comprehensive digital twin is the key to both planning and execution of new production, but also for keeping current production under control, predictable, even during dynamic stages. A closed-loop digital twin, which allows and relies on new data being fed in from the actual production, is very important in order to create a comprehensive twin and maximize efficiencies. Once this is done, we can start to look at the workflow of constructing manufacturing systems and make it simpler and more efficient. We expect that the workflow of future manufacturing will look very different from today. Today, we go through sequential, iterative, and manual processes for engineering, and with great separation between different disciplines and departments, like mechanical design, robotics handling, electrical, and automation planning. These all happen one after another, taking a long time, but also requiring many different cycles. If a change happens, if a mistake occurs, this sends us back to our drawing board and takes a long time to get started again. With the digital twin, processes can be prepared digitally and in parallel. Higher quality results can be achieved in shorter times, helping us live up to today's challenges. The design phases, as mentioned above, can happen in parallel to each other and be tested all together much earlier on, in the end leading up to a lot of time being saved and a lot of money. With all that in mind, I want to show you a part of the Siemens software portfolio and how our tools, specifically Process Simulate, can help users navigate these challenges, turn it into benefits. Process Simulate offers a wide variety of tools and applications for designing, maintaining, or analyzing the digital twin. I'll take a stepwise approach to walk through this, although as I mentioned before, each company's road toward digitization is in the end unique and can differ from each other. Our first step includes building the digital twin, but also making first use of it. It includes the various modeling, kinematics, or physics capabilities that allow us to build our digital twin in an accurate manner and use it in early engineering phases for layout planning, footprint estimations, reachability studies, or other early engineering concept validations. All sorts of manufacturing processes can be realized and engineered, like welding, handling, palletizing, cutting, and others. The results of these early engineering phases are then taken to the next level with robot offline programming capabilities for all major robot brands in a single working environment. And finally, toward automation validation using either a hardware or software in the loop approach. This full-blown range of solutions within a single integrated work environment allows engineers to focus on their work and collaborate easily. They have a common language they can speak. This is not to say it's an easy step. We all know often first steps are the most challenging, but already within this first step are great opportunities. Let's take a look at such an example. In this case, a digital twin is built for a production machine of a robotic assembly for electronic casings of automation equipment. This is a subject well known in Siemens, of course. This digital twin includes all necessary information like layout, robotic information, behavior models, kinematics, and physics. In this last step, the virtual cell is connected to a virtual PLC using PLC Sim Advanced and WinCC for the HMI controls, offering an operator fully realistic environment to work in. A typical use case is testing for safety. In this case, we want to test for fail-safe and emergency situations. We can see that when triggering the door opening by the operator, safety isn't triggered and production of the machine doesn't stop as planned. This is a critical error that we must take a look at. In this case, we'll take a look at the PLC code while staying online with the simulation. This helps us emulate what we can really do even in production. Here, we need a correction in our PLC code. Apparently, either a mistake or an oversight is made. We can make a change live inside our digital twin in our virtual PLC, download it, and revalidate again. This time around, when we power on the sequence and put the cell into automatic production, we can see that opening the door, as expected, will make production stop entirely. The operator also cannot reset this fault unless he clears the door again, meaning closes it and then hits the relevant button inside the HMI. This gives us a 3D environment realistic enough to test our safety situations in. The motion stops, and there's no way for the operator to do anything until it closes again. After it closes, we can restart and check that the line can ramp up again and production can continue. This is just an example of a workflow, but of course, a realistic digital twin enables us to test for a lot more situations, as many as we want to prior to going down to production. The next step in this program is cloud. I won't focus too much on this point today, but I know this catchphrase is used quite freely nowadays. In Siemens, we strongly believe that in order to take this next step in manufacturing, an open and personal ecosystem has to be developed. And as I mentioned before, collaboration is a huge key to that. Consider even just the example we were just looking at for virtual commissioning of a robotic cell. Such a task involves robotics, automation, and simulation engineers all working together. We have to provide a collaborative environment for them to be looking into together. The Accelerator Share portfolio from Siemens enables a cloud-based environment, providing users collaboration which is both secure, up-to-date, and also easy. Users can reach the most up-to-date data from anywhere and with little or no IT effort, so they can focus on their actual work and on creating an excellent engineering network. I mentioned I won't dive too deep into this topic, but if you're interested to learn more about it, it's easy. Just look it up online or contact your local Siemens. Step 3 is the integration of advanced robotics into the digital twin in order to facilitate flexibility in production, like we discussed in the beginning. Flexibility is the main differentiator between today's and tomorrow's production needs. You can see an example in this slide of what we expect production will look like in the future. Not that far future, it's rather close. So special focus is placed on certain topics like autonomous vehicles for intralogistics, AGVs and AMRs. They allow incredible flexibility and are fast becoming very common in many manufacturing areas. Process Simulate includes tools to plan, validate, and optimize AGV motion, alongside connectivity to fleet management systems for virtual commissioning, integrated directly in our digital twin. Another main topic are computer vision technologies for guided robot motion, but also for other applications, which allow reactive robotics and lower costs for special tooling in production. We'll cover vision more deeply in a couple of the next slides. And maybe last but not least is this topic of human-robot collaboration. Integrating robots into a worker's environment, it poses certain challenges and dangers, but it can also gain great benefits, like healthier work environments for personnel or greater efficiency, all the while trying to maintain production flexibility and performing tasks which are too difficult to automate yet, alongside tasks which are easily automated using robots. Let's take a deeper look at one such example for computer vision. This example comes from our customer MechMind, who's a robotics vision vendor and integrator. As such a company that manufactures their own equipment but also integrates it in production, they face these exact challenges we've been talking to up until now. By using a digital twin based on Process Simulate as an open platform for integration, MechMind are able to simulate all kinds of scenarios upfront, gaining great savings. The digital twin is used in all stages. First, during early phases, when designing the layout of the station, the robot, the camera, and all other peripheral devices can be positioned in a virtual environment and adjusted accordingly. Early reach studies can help pinpoint the optimal position of the robot and other devices too. After this, static testing can be easily and graphically done. This allows easy testing of various aspects, like end-of-arm tooling. In a bin-picking application like this one, the validation of the end-of-arm tooling, the gripper, selected for the job is paramount. In this case, we can clearly see that the selected gripper doesn't offer a good range of motion and flexibility, and it must be replaced. So a longer and narrower model can be selected, and the evaluation can continue. Now we're ready to simulate a first dynamic scenario. We can use the modeling capabilities in Process Simulate, in this case physics simulation, to generate random part distributions for this cell. A virtual image can then be taken in Process Simulate. Both RGB but also depth information can be retrieved and transferred to a software version of MechMind's camera. MechMind are able to use the digital information to create results. From the camera's point of view, this resembles reality so closely, it allows us to test the real behavior of this system. The robot program kicks in, moving the robot to the target position, picking up the various parts. This can be repeated, allowing us to explore various scenarios with the digital twin, analyzing results and asking ourselves, how many parts are reachable? What is the pick rate and the pick success rate for this application? If we identify any issues or bottlenecks, we can work to fix or optimize them in the digital twin until requirements are met. In this case, the pick rate was too low, and many parts simply could not be picked up. We adjust the robot program and alter the relaxation ratio, which controls the gripper angle, allowing us to complete the process. After virtual commissioning, the operation of the actual production station can be started smoothly. Our next step is to take our digital twin with the integrated advanced robotics technologies and use that to enable looking into the future toward mission-based production. This kind of production is not pre-programmed. Rather, it's based on creating a work environment where a new task can be handled by the existing facility and controls. In the future, this will lead us toward more autonomous factories, which are flexible, dynamic, and also self-adjusting, being based on the Internet of Things, analytics, and autonomous robotics. A great example for this is the integration of real-time robotics in the challenging task of robot motion planning for automotive welding lines. Welding lines pose a double challenge, both in terms of complex work environments, geometrically speaking, alongside ever-lowering requirements for smaller cycle times and greater accuracy. All this means that programmers have to be very proficient and innovative to stay in the game. Real-time robotics offers an AI-based live approach toward robotic path planning, as shown here at Valiant TMS. This is a leading global system integrator and a longtime Siemens partner. The digital twin plays a double role here as well. On the one hand, it allows an integrator such as Valiant a risk-free environment to experiment with new cutting-edge technology of high potential. This is exactly what we mean in Siemens by talking about an open ecosystem. Full evaluation of this technology can be made virtually, playing a key role in enabling organizations to step into digitization and unlock great potentials. The digital twin also allows making this new technology predictable and enables including it into the overall engineering workflow and processes. In this example, you can see how the digital twin can be used for both purposes. We start off with a welding station in Process Simulate, for which early engineering phases are done. This means we've laid out the components in the station and have generally already designed the welding process. By simply connecting the AI, we can immediately step into a fully functioning workstation, including both collision-free motion for the robots and interlocks. This saves us a ridiculous amount of time, which is usually spent trying to adjust motion in order to meet requirements. And the best of it, it can be done virtually well before any actual building phase by using a digital twin. This digital twin is also flexible. If any change occurs, like the introduction of a new product variant or a change in the layout of this station, the system can simply recalculate quickly. This really lets users realize the vision of future manufacturing becoming more mission-oriented and flexible, and all that even virtually from the comfort of your office or home. So if I have one message to deliver in today's talk, it would be that we in Siemens invite you, our customers, our partners, but anyone else to take a first step with us in this journey toward digitization. By employing a comprehensive, realistic, closed-loop digital twin, you can gain great benefits on the road toward production excellence. Also embed new emerging technologies really rapidly and keep up with current trends, facilitate the integration between different disciplines and departments and even companies, all based on the Siemens open ecosystem. One way you could go about this is to try out Process Simulate yourself online. There's a 30-day trial, free, including video and training material that you could use on your own to get started. You can easily find it by using your favorite search engine or just scanning this QR code here. And with that, I'd like to thank you very much for taking the time to join the talk today. For the Process Simulate product management team and myself, I hope we'll see you again in one of our next events. Thank you very much.
And I would like to thank our attendees for joining us. You will receive a follow-up email with a link to view the recording of today's session. So you can, of course, watch that again, and please do share that with your colleagues as you see fit. If you think of any additional questions or need to request materials, feel free to email me directly, sarah.alspaugh@siemens.com, and I can point you in the right direction or forward you to where you need to go. If you do have a project immediately in mind, feel free to give us a call and we can help you get started right away. And this concludes today's webinar. Thank you so much for joining us, everyone, and have a great rest of your day.